Hello everybody, my name is Stefan Kohl and this is my talk, Harnessing the Power of Unity's Asset Pipeline. I will first give you a little bit of introduction about myself and my motivation behind this talk. Before I will explain briefly how the Unity Asset Pipeline works. In the second part of my talk, I will bring some practical examples based on scripted importers and asset post-processors. All right, then let me start by giving a little bit of background about myself. So I started using Unity in 2013 as a hobbyist. Back then, I was mobile games developer using low-level C++ game engine, writing 2D casual games for mobile devices. And in 2016, I decided to quit my job because I want to focus more on developing 3D games in Unity. During my time as freelancer, I also had the chance to work on a few Unity VR AR apps and also start my hobby project, Sikanda. In 2019, I relocated to Taiwan and started my indie game studio, Dyadic Games, over here. Together with a team of dedicated people based here in Taipei, I rebooted the Sikanda project with them, and this is what we are working since now. In addition to that, we also have a second product in the pipeline that's called Stylus Word Factory, which is a procedural content generation tool based on Houdini that can be used in Unity to create stylized environment assets. So why am I talking now about the Unity asset pipeline, while there are some more interesting things to talk about when it comes to Unity? Well, if you find yourself in the same situation as ourselves, like being an indie game company with a very small team and very limited resources, but you have a very ambitious and asset-intense project, then you know that wasting resources is something that you absolutely should avoid and cannot afford. If you want to figure out if the knowledge I want to share here with you based on my experience is relevant, then just ask yourself, suppose you want to onboard a new team member who is going to join soon to help you with your indie game project. And the role of the team member will be to integrate assets into the game to make them ready for use with the different systems you have, so that, for example, the objects, monsters, or NPCs can interact with the systems. And in order to make this happen, you have to follow some certain steps, like attaching certain components and do some certain configuration. And if this is at a point where you need to provide a step-by-step guideline to hand over this knowledge, then consider not writing this guideline, but write a script for the Unity asset pipeline that does this for you. Now, in order to understand what the Unity asset pipeline does and how it works, we need to go through a few definitions, with the first one being to answer the question, what is an asset? You will most likely be familiar with that already. So an asset is an item that you can use in your Unity project to create your game or app. This is what the official documentation says. Assets can represent 3D models, textures, sprites, sound effects, or music, but they can also represent some more abstract objects like animations or any kind of data that is relevant for your game or for your game systems. The documentation further states that assets can be created inside of Unity or outside of Unity. And when we dig a little bit deeper, then we find this distinction between native assets and foreign assets, with native assets being defined as files produced directly by Unity's serialization system. And you most likely also already ran over to native assets when, for example, dealing with materials or meshes or animations, which have their distinctive file extension. And in case you've opened these files in a text editor before, you could see they are all written in the YAML file. That is what Unity by default uses to deserialize and serialize its assets in a text format. Your scriptable object-derived classes, so the classes that you write when you want to have your own asset types, are also considered native assets because they use the same serialization system. However, scenes and prefabs are different. They are considered foreign assets. And the reason for this is because they want to take advantage of the asset pipeline that is available for foreign assets. We will later take a look at that. So a foreign asset, according to the documentation, is an external file that you import into your Unity project. For example, a PNG texture. An external file means that it was created with a program outside of Unity. And when you import a foreign asset, Unity will produce a serialized representation of the data in the project's library folder. So let's see an example on how this looks like in Unity. We have an FBX file, which is a foreign asset. So Unity cannot directly handle FBX models by itself. It needs to go through an importer, and this is what we see over here. So you can apply different settings on how Unity should import the object. And once it's imported, it will somewhere end up inside the library folder. This is what we know so far. Now, how does Unity import an asset? The documentation again says when you modify a file in Unity, Unity does not modify your original source file. Instead, the import process reads your source file and creates a game-ready representation of your asset internally, with internally meaning the library folder specifically. So there's a lot to take from these two sentences, and we need to dissect this a little bit. So let's see what creates a game-ready representation of your asset means. So we have the asset, and we want to turn it into a game-ready representation. There's obviously some process in between. But what exactly is this? So the game-ready representation is called an artifact, and the process is driven by importers and post-processors. So we have three new terms here that we need to clarify first to better understand what these post-processors and importers and artifacts are. Let's first take a look at the importers. There are two different types. The first category are the built-in importers, and the second one are the scripted importers. The built-in importers, as the name already implies, are shipped with the Unity editor installation. And they are further classified in built-in native importers, which are written in C++, and the built-in scripted importers, which are written using the C# API of Unity. This is exactly the same API that you can use to create your own scripted importers, which falls into the second category, the one that are not built into the Unity editor. The second component we introduced before is the post-processor. So when the importer has done its job, then the asset file now is available as a game-ready representation over here. But it's possible to further process this game-ready representation using post-processors before the representation gets serialized into an artifact, which is the final result of the importing process. Now, what is an artifact exactly? An artifact stores serialized Unity engine objects for each asset. So we know over here we have the asset. It goes through the import and the post processor. It becomes the artifact. And when we deserialize the artifact, we get a bunch of Unity engine objects. Unity engine.object is the base class for all objects Unity can reference. And this is very important to understand, especially when you compare them to regular C# objects, which are objects that the Unity engine, the C++ part of the Unity engine, is not aware of. So in order for the engine to reference your assets, they need to be available as Unity engine objects. Now, let's summarize what we've learned so far. So we know that native assets can be deserialized directly in the Unity engine.object, while foreign assets need to go through the import and post-processing stage to be then serialized into an artifact, and artifacts can then be deserialized into Unity engine object. So let's see how this looks like in the Unity project. For example, we have, again, this foreign asset over here, the cube. which we can also show in the Windows Explorer and review in the Windows file viewer. So that's indeed what is inside this FBX file. What we now see over here is the result of the import process. And again, the FBX importer is using this property that we set over here. But what I want to show you now is how the post-processing comes in. And for this, I've prepared post-processor. So if you want to write a post-processor, you need to derive it from the class asset post-processor. And depending on the asset type you want to post-process, in our case, it's a model, you need to implement one of these callback methods. In this case, it's the onPostProcess model, which takes the game object that the importer produced as an input. So what we do here, we filter first out all the objects that don't contain the label cube. So we only want to handle objects that are labeled with the cube label. And then we analyze this object and find mesh filters or game objects inside this this main object that is not named cube. So we clean it up basically from anything that is not a cube. And as you've seen before, we need a label for this in order to trigger the post-processor. And now you can see with the post-processor applied, the imported object that we see over here has changed. So it looks like the cylinder object that we had before is missing. But when you check the file in Windows, it's still there. And this is what Unity was mentioning before when it says it does not modify your original source file. It creates a game-ready representation of your asset. So why am I explaining you this? It is very important for you to understand that what you see over here in this project window in Unity is not the files that you have in your Windows Explorer when you click over here and show an Explorer or similar on the Mac with the Finder. What you see over here is the result of importing the asset. And as you can see with asset post-processors and scripted importers, you have total control over what ends there up. And I want now show you how you can use this control in order to make your workflows more optimized. Let's talk about scripted importers first. This is a way to make Unity understand your own custom asset format that it otherwise could not handle by itself. So as a first example, I want to show you how to create procedural assets, more specifically procedural meshes based on a custom file format. For example, you can create a custom file format to save level structures inside. Maybe you have some kind of labyrinth game and then you have a labyrinth prepared as an SVG graphic and you write an importer that creates walls for labyrinth out of the SVG. For this example, I choose something simpler. I want to create a star importer that handles .star files. This is basically a JSON format which describes these stylized stars, like the example over here. And it is described as three properties: the outer radius, which is the radius of the convex corners, the inner radius, which is the radius of the concave corners, and the number of corners in total. So let's take a look at how these JSON files look like. So that's star_1.star. The three properties I mentioned. Yeah, nothing really exciting, just plain simple JSON file. How can we import a file that Unity doesn't know into our project now? For this, we need to derive our star importer from the scripted importer class that is provided by the Unity editor. And we need to add the attribute scripted importer where we define the file name extension that we want to apply the importer on. In addition to that, very similar to scriptable objects and mono behaviors, you can define serializable properties that can be set at the importer. Like when if you remember the FBX importer, you have a bunch of properties for importing your model. And you can do the same with any kind of importer that you write by your own. So in this case, I want to set the color in the importer directly, as well as the depth, so how thick the star should be, and then apply some uniform scale to it. Now, what happens over here is we read the JSON file, we get the properties from the JSON, then we have a method here that procedurally generates the mesh based on these properties. So I won't go into details because if you're interested, you can check it out on GitHub anyway. And once we have the mesh, we of course also want to have a material because we want to render it somewhere. And in order to render it, we need, of course, a game object, a mesh filter, and a mesh renderer. So after we created these 5 objects, we need to set them up accordingly and connect them with each other. We further apply the color that we set at the importer to the material, as well as applying the uniform scale. And the depth is already considered in this part over here. The final step of the import process is to add the objects that you generated to the context that gets passed here in this callback method on import asset, and define what should the main object of this asset be. The main object is the one that appears as the root object in the project explorer. If you remember the FBX importer or any kind of model importer, they will show a game object with the mesh asset inside the game object being nested as a sub asset over there. And we want to do the same. So the goal is that once the asset is imported, we can simply drag and drop it into the scene and use it right away. And the result looks exactly like this. So we have here our star files. So 3 different stars described by the JSON attributes. Additionally, we use the settings we defined in the importer directly. So we can see the color that gets applied to over here, as well as the depth and the uniform scale. And what we can do now is just drag them into the scene. And we see these cute little stars over here. Now, when we check the assets again, there is a mesh in the material, and additionally, the components that the game object has attached to it. When we now again check at the file explorer, there is still only the JSON file and the meta file that contains the importer. The question now is, where is the mesh saved? As you might already guess, this is where the artifact comes in place, because the artifact is, as mentioned before, the result of the importing. And in order to get a little bit more insight of what's happening when Unity imports this asset, we open a very handy tool called the import activity window, where we can see all the imported assets, including the time when they were imported and how long it takes. We have some general information here that you can also find out mostly in the file explorer. And what's now very interesting is the artifact that got produced, which we can reveal in the explorer. And now we can see this is inside the library artifacts folder, just as we mentioned before. In addition to the artifact, we have the information about its dependencies. And don't let the word dependency confuse you, because dependencies in this context just means it's a list of properties that uniquely describe these artifacts. And whenever one of these properties gets changed, a completely new artifact needs to be generated. And these artifacts, they will stay inside your library folder until you restart Unity, for example, when they get cleaned up, or until you delete the library folder and they are completely gone. Yeah, for the dependencies, there is, for example, the hash of the meta file or the hash of the source asset, which means when you change something in the meta file or in the source asset, then a new hash gets generated. And as mentioned before, changing any values over here will trigger to generate a new artifact. And this is exactly what we want. Like when we change some settings in the importer, for example, the color over here, then this change of color gets written in the meta file. And we can now see, when we list all the imports, that now we have a different hash for the meta file while the rest stays the same. And it will produce a completely different artifact. Also, when you change the file name, it will trigger re-import. This is important to understand because the post processor, for example, might take the file name into consideration as well. In order to prove what I said before, I want to use a tool that Unity ships with, which is called the binary to text tool. And you can find it in the installation of the editor inside the editor data tools folder. So let's use it. What it does is it takes the artifact file as its first input, and it will generate a text file out of this binary artifact file. So the text file that is generated is just a textual representation of the binary. And this can be used for debugging or just if you're curious and want to understand what's inside the artifact. And the things we find in the artifact, for example, the mesh with all the vertex and index data, as well as the mesh renderer, the transform, the game object itself, the scripted importer, are exactly the objects that we find over here. We also have the mesh filter, the material, which is this one. And finally, the prefab, which acts as a container for the game object. Now, another example for scripted importers I want to show you is how you can create databases that were produced with external programs and be converted into native Unity objects. Suppose you're working with a game designer and the game designer is producing the databases in maybe in Excel or Google Spreadsheets. And what they provide to you is a CSV file that you want to get integrated into your Unity project. Ideally, when you have a data file, you want to use a scriptable object derivative. For example, if the game designer is handling the enemy data for you, then you want to put this enemy data into some enemy data class that is derived from scriptable object. So the first way, the very simple one you can do is just copy paste the values from the CSV file to the scriptable object file, like this, what I do now. So we create an enemy data. It's a scriptable object. And we have here the CSV file that was provided by the game designer. You can see it is a bunch of enemies defined with some basic properties like health and strength and also a name. And now we want to get the first enemy into Unity. So we copy the name over here. The health was 20 and the strength was 1. And now we have the data set of the very first enemy over here. Now there are 20 left, and maybe depending on the scale of your project, there might be 200 or even 2000. And you might also have a lot more properties than over here. So you can see this way doesn't scale very well. For that reason, and this is something I see very often in discussions on the official Unity forums, people write their own parser to handle CSV files because they don't want to lose the convenience of getting the files that are produced by other team members, just putting them into Unity and then load the data from over there. Because in terms of workflow, it's still the quickest way. So we don't want to spend time on manually writing these scriptable objects, right? But there's one issue with this. So the first one is that the CSV file needs to be placed in the streamable assets folder. So it's no longer part of the Unity asset system by itself. And when you parse the database at runtime, this means you create a second data management system in parallel to the Unity asset system that is also used to manage data. Like as I mentioned before, you can use scriptable objects to define assets that simply represent data for your game systems. But this is not what you do here. You create a second system. Basically, you parse the CSV files in runtime, which is much slower than when Unity deserializes artifacts or general native assets. And it also has the disadvantage that you cannot reference these objects anywhere. even if you create scriptable objects at runtime, you won't have the convenience to reference them in the editor itself. So is there a way to combine these two worlds and use the best of them? And yeah, it is. It's the third solution I want to show you, which is based on the scripted importer. So we still want to have the CSV file be used directly in the Unity project so that the game designer can just hand us over their files. We put them into the Unity project, and thanks to the scripted importer, we can now create the scriptable objects automatically with a custom scripted importer that you write. This is what I'm going to show you now. So if you remember, this is our CSV file. We have the enemy database importer. This just reads the content of the CSV file, and for every line it finds in there, it will create a scriptable object, namely the enemy data. And the result looks like this. So we have the CSV file over here, and all the enemy data objects, which are qualified Unity engine objects that Unity can reference to and can deal with, are just added as sub assets. So the asset that we first created by ourselves manually is now conveniently imported for us by our scripted importer. You might not always have the requirement of introducing your own custom asset formats just to get your workflow be more compatible with how Unity works. There are also other ways of doing it. For example, using asset post processors to further modify assets that Unity already can handle, most likely models and textures or any other kind that might be relevant. And the first example I want to show you is for setting up specific objects that belong to a specific category of your game. A category might be a monster object or item object, NPCs, props, whatever. It's up to your game. And if your game is like as huge as ours and has a lot of subsystems, you might choose a component-based architecture, which means all of these different objects have a lot of components attached to interact with these different systems. And getting one object ready to be fully integrated in the game might involve a long setup process where you need to go through every single object and set up a lot of components, maybe manually calculate or determine some of the properties, which is quite tedious and also prone to errors because humans just make mistakes. That's how it is. And when you have this automated process, you can not only save time, but also avoid these mistakes from happening. So let's see what this means. Let's first use a monster model over here that doesn't have any post processor. So I just added the ignore label over here. It only has the basic components attached to it. And now I want to make it ready for interact with the game systems. So I add a bunch of components to it. We also want to have a character controller, and there might be some project-specific requirements for the character controller. For example, it has to have a radius that is half of the bounding box or half of the smaller side of the bounding box and exactly the height of the visual bounding box like this. Depending on your project standards, you might be even more rigorous in setting this up. So there might be some calculation involved as well. Yeah, we might also need to set a tag for it as well as a layer because our game systems require it. And now you can see after these steps, we have one object ready that we can save as a prefab and then continue with the next one. It's fine if you only have one or two of this category, in this case, monsters. But suppose you have like 20 or maybe 100 and you have a lot of components to set up, then this will create a lot of overhead and will be hard to maintain in the long run. Specifically, when something of your game systems is changing, then you need to go over through each single prefab and set them up again. So the way it's done in a more efficient manner is using post-processors. This is the one I prepared over here to demonstrate. So it's again an asset post-processor called enemy model post-processor. We implement the on-post-process model method. We only consider the models that are inside this example folder. We don't consider models which are labeled with ignore. And then we do the setup over here, basically exactly the setup that I did before. So we set the tag, the layer, we add the relevant components, and we do a little bit of calculation for the character controller. So to get a nicely dimensioned capsule around the monster. And as you can see, doing this by hand is quite annoying. And if you make a mistake, then you might not even find out that something is wrong until proper testing. Now let's remove the ignore label again. And when we check the FBX file over here, it now has all the components attached, including the character controller with the proper dimensions, as well as the label and the layer set properly. So we don't even need to create a prefab. We can just drag the game object that was generated from the FBX file directly. And it is ready for our game systems to use. Now, a second useful example for asset post-processors is when it comes to platform-specific asset variants. Suppose you have a FBX file with three different models, and each model represents the same object just in a different mesh resolution. And depending on the platform you are deploying it, you want to show a different resolution of the mesh. So you want to have a high poly mesh for the standalone platforms, mid poly for console platforms, and low poly for mobile platforms. There are, of course, a lot of ways to do this. You can do it just at runtime. So you have a component, and when the object gets initialized, you switch the mesh from the mesh filter based on the platform where you're currently on. Another way is using build post-processors or scene post-processors. But in my opinion, the more elegant way of doing this is using an asset post-processor, because the asset post-processor happens during the import stage, so only once, not every time when you build the game. And furthermore, if we have this model, which I'm going to show you now, so I will add the ignore flag so we can see the original famous Blender monkey. We can see we have three different models inside here, each with a different resolution. And what we want to do now is that depending on the platform we are at the moment, and right now it's the standalone platform, we want all the other meshes to be removed during the post-processing stage. So let's remove the ignore label again. And we can see we now have a single game object with a single mesh inside. That is the high poly mesh that we want to use for the standalone platforms. Now, let's switch the platform. Maybe let's put it in the scene first so you can see more clearly what's happening over here. And add the selection wire. So yeah, I think over here it's quite good. We're on the standalone platform. Let's switch to Android. And you can see exactly the same game object that we dropped over here now suddenly has a completely different mesh. The same for the iOS platform. Uses also this low or mid poly mesh. And when we go back to the standalone platform, we have the high poly mesh again. And you can see over here, this still remains unchanged. So the object you see in the Unity editor is exactly the one you will see in the final build. You don't have to use the high poly mesh whenever you're in the editor, and then it gets swapped out with a low poly mesh on the runtime platform. And another interesting aspect is when it comes to build size optimization. So let's take a look at the imported model again. And let's see the history of the different artifacts that were generated. We are now on the Windows platform, which means our artifact is 1.4 megabyte. And this is exactly the same artifact that will be shipped with the build when we create a standalone platform build. The second artifact in the history is the one that was generated when we switched to the mobile platform. And this only has 410 kilobytes because the mesh that was used over there had a much lower resolution. So the interesting thing now is when you compare to the original asset that has all three meshes inside, which is 1.8 megabyte, that for the low-end platforms, we have greatly reduced size of this asset. And this is a big advantage over the other approaches that when you ship all the different model variants together and then just pick at runtime, because now you also have the control on which kind of assets will even end up in the final build. So it's not only an improvement on the runtime performance, but also on the size of the build itself. Speaking about runtime performance, there are different techniques that game developers use, for example, to improve the performance of shadow mapping or the performance of physics simulation with mesh colliders. In terms of shadow mapping, there is a technique called shadow proxies, which means instead of using your high poly render mesh, you create an approximated mesh with much less details that can be used for shadow rendering. So when you have less polygons for rendering a shadow map, then of course it will be faster as well. The same can be said for collider meshes. If you don't use the high poly mesh for mesh colliders, but create some low poly approximation like the one we see over here, then you can make the physics simulation much more performant. But this means your artist has to prepare 3 different models, and in Unity, setting up these models to include all the performance optimizations. So we have the main render mesh, and we want to don't render the shadows from this one. Let's add the mesh collider with the collider mesh. So this one we need to remove, and the shadow proxy should only render shadows. So you can see the main object is not rendering shadows, the shadow proxy is only rendering shadows, and the collider mesh is over here, and this is our optimized game object now. It is a little bit annoying to set it up. I mean, it didn't took me too long, but your project might have several hundred or even several thousands of these assets, and doing this manually would just waste too much time. So let's write a post processor for that. That follows the simple convention that when there is a child object with the suffix minus collider, then it will be used as a mesh collider. And when there is a child object with minus shadow proxy suffix, then it will be used as a shadow proxy object. And it will also turn off the shadow casting of the main object and use this one with the shadows only rendering option. And finally clean up the objects that are no longer needed because they just serve the purpose of, or they just were created by the Unity default importer. So let's remove this and remove the ignore label. And now we can see, maybe as comparison again. Let's the ignore label back. This is how it looks like with the ignore label, and this is after the post processor did its job. So the setup I did manually is now already applied to it, thanks to the post processor. All right, this is the end of my talk. I hope there was something useful you could learn and probably apply to your own projects. In my opinion, the Unity asset pipeline is a very powerful tool, but its potential is very often overlooked. And I think game developers, especially indie game developers, should spend more time understanding what the asset pipeline can actually do for them to make their life easier, especially when they have a game with a lot of content or lots of assets inside. And the other thing you need to understand is if you work with a team, or even if you're a solo developer, as an indie game developer, you do this because you love what you do. And you don't want to annoy anybody with some boring tasks. So I think the goal of the indie community is to, or people from the indie community is to do some creative tasks or solving some interesting technical challenges, but not doing some repetitive, boring tasks that a computer can do for you. In this case, the Unity asset pipeline. So before writing step-by-step manuals on how to integrate your assets into your game system, write code for the Unity asset pipeline. Thank you very much.